Hey everybody, welcome to this video. This is going to be our last video on one-dimensional equation. Before we were talking about deriving this kinematic equation where we have a constant acceleration, and this is super useful. But what if we run into situations where acceleration is variable? If acceleration is changing with time, can we really just use one equation? Well, what do we do? Well, to kind of answer this question, let's just dive right in with an example. All right, so let's say you're in your car, you're at a stoplight, so you're not moving, so from rest means your initial velocity is 0. And then you accelerate for 4 seconds at a rate of 5 meters per second squared. Then you're going to cruise for 10 seconds, so your acceleration is going to be 0. You take your foot off the gas pedal, and we're going to ignore friction. And then after 10 seconds, you start braking, causing the car to accelerate at negative 10 meters per second squared until the car stops. So the question is, how far did you go in your car before you came to a stop again? All right, so you can see that this really has 3 parts, right? The part where we're accelerating from 0 to 4 seconds, the part where we're cruising, and here acceleration is going to be 0, right? And then at the end, from 14 seconds until we stop, where our acceleration is negative 10 meters per second squared. All right, so there's, a few different approaches you could have to this problem, but I wanted to try illustrating this graphical approach. So with the graphical approach, we're going to make a plot of the velocity over time. And so we're going to remember that acceleration is the derivative of velocity. And so you can write out that the velocity is going to be, your initial velocity plus time times acceleration, right? And so you can think, since time is multiplying by acceleration, it's like time is our horizontal axis and velocity is our vertical axis here. So acceleration is really going to be the slope of the line. So let's start our velocity plot, right? With velocity on the vertical axis here, time on the horizontal axis. You can see this goes up in increments of 5, conveniently. So we're starting at 0, right? And we have a slope of 5, right? So we go up 5 meters per second for every 1 second we go across. And we continue on that slope for 4 seconds. And then we have an acceleration of 0, which means the slope of our line is going to be 0. So we're flat. And obviously you can think, oh, the acceleration is 0, so you know that the velocity is not changing. So we're going to stay at 20 meters per second for 10 seconds. And then, right, we're going to switch to this negative slope as our acceleration is negative. And we're going to go down 10 meters per second squared for every 1 second we go across. And do that until the velocity reaches 0, which conveniently is after an increment of 2 seconds braking. All right, so we've drawn these lines here because this is interesting, because we can remember that, oh yeah, velocity, that's the derivative of position with time, which means that position can be found as the integral of the velocity over time. And the integral, what it's actually doing is it's kind of taking the area under the curve, so between the line and the x-axis, or the horizontal axis. So what is the area of this section of the curve, of the part where we're accelerating? Well, that's the area of a triangle. So you take the height of the triangle, you multiply it by the width of the triangle, and that's 1/2 the width times the height, so 4 seconds times 20 meters per second. And so the change in position over that portion of the curve means we're going to be moving 40 meters ahead of where we started. And for this area, this is just the area of a rectangle, right? And that's taking the integral of this portion of the velocity curve. So it's just a rectangle, so it's the height, 20 meters per second, times the width, 10 seconds. So over that time period, right, traveling at a constant velocity of 20 meters per second per 10 seconds, so we travel 200 meters. And over this portion, this is another triangle, right? So the area under this curve is going to be the width times the height times 1/2. So over this portion, we continue to move forward 20 meters by the end and by the time we reach a stopping point. So if you'll recall from a couple lectures ago, the total displacement is just going to be the subsequent displacements added together. And so in the end, we've traveled 260 meters throughout this process. All right, so that's an example of using the graphical approach to kind of solve this three-part 1D kinematics problem. And you could also just straight up use the kinematic equations too. You just kind of have to do it in 3 parts. So I wanted to demonstrate that. So you have to treat each part by itself. So we're going to say at, in this first time period where we're accelerating, we set our initial velocity 0 and x naught is 0. So this term goes to 0. And this term goes to 0 because v naught is 0. So how far have we gone in 4 seconds? Well, we're going to have an acceleration of 5 meters per second squared times 4 seconds squared. And when you plug that in, you can see that we travel 40 meters, and that's the same as we derived with this graphical method here. For part 2, we have to keep in mind where we just finished, right? We finished 40 meters ahead. So we're going to say x2, our position after part 2, is going to be our position at the start of part 2, which is the position at the end of part 1, if that makes sense, times our, what is our initial velocity at the start of part 2. It's going to be whatever the velocity was at the end of part 1. Plus the acceleration. So in part 2, acceleration is 0, so this term goes to 0, right? And what is our velocity at the end of part 1? Well, we have to just quickly calculate that, where we were accelerating by 5 meters per second squared times 4 seconds. So like we said in the graph, our velocity is going to be 20 meters per second. So we plug that in, and we're going to see that we travel an additional 200 meters, so our position at the end is going to be 240 meters. All right, now we think about part 3. So our position at the end of part 3 is going to be our position at the end of part 2 plus whatever changes happen. So we need to think about what is our initial velocity at the beginning of part 3. Well, it's actually going to be the same velocity that we came in with since we weren't accelerating during part 2. So v1 is going to be equal to v2 here. So we're still going to be moving initially at 20 meters per second, right? We're kind of at this point up here. And then we have to think about our acceleration, of course, which is negative. And so when we plug in the numbers that we know, we know this and we know what acceleration is, but what about time? How much time passes during part 3 when we're braking? Well, we solve for it graphically, but to kind of solve for it algebraically, we use this expression again, right? The velocity is going to be your initial velocity plus your acceleration times time. And what's our velocity at the end when we stop? Well, after we brake and we stop moving, our velocity is 0. So we plug in 0 for this value here. And this is 20 meters per second, our initial velocity. So we move this over to the other side, and we have 0 minus 20 meters per second is going to be our change in velocity. And then acceleration is negative 10 meters per second. We divide both sides by the acceleration. So we have negative 20 divided by negative 10. It's going to be 2 seconds. Like we saw up here, this braking period lasts for 2 seconds. All right, so when we plug that in, we can see that our change in position, or our final position after X part 3 is going to be 240 plus 40 meters minus 20 meters and 260 meters. The exact same answer that we calculated with the graphical method. All right, so both methods are valid. And we're really doing the exact same thing, except, with the graphical method, we kind of conveniently solved for some things without having to do the math. We just kind of let the plots do the math, calculating our velocity after part 1, and thinking about these integrals was a convenient way to think about how much displacement occurred during each acceleration time period. All right, so see you in class.